As promised in the last video, we're going to be looking at the back panel today. This is where all the electrical in and outputs for the instrument are, plus a little screen to show things like the mode, settings and other useful info for setting up the thing. This part of the project was largely an exercise in CAD modelling rather than electronics, and thinking about the way that I wanted things laid out. For me, the fun part is the electronics, but sometimes you just can't have your EVI and eat it too. A lot of the time in CAD modelling was spent measuring the components that were going into the panel and then making models of those so that I can build an assembly to see how it all fits together before I go ahead and print it. I love the sound of the squealing stepper motors on my 3D printer so much that I always print early in the morning so that my neighbours can appreciate the singing too. After that was all said and done, this is the back panel structure that I came up with. It's got space for all the parts I wanted to fit in, and as far as I can tell, fits pretty nicely. I'm taking the approach of building the EVI in sort of modules so that I can design it in a more incremental way, and don't have to worry so much about getting it all right on the first pass. This module has some screw holes for mounting it into the body of the final EVI, just like the rotary encoder in the last video. Something I always do when I need to get things to fit well is I make a test sample of different hole sizes. These are just holes that are incrementally increasing in size or proportions so that I can feel what the final fit will be like after the part is printed. It saves a lot of time with parts that are badly fitting, and though the upfront time cost is bigger, the longer term payoff is better, as is almost always the case when you design a product. While 3D printers are generally really good for accuracy in their prints, they do have a big disadvantage, which is that 3D printed parts are not really modifiable. If your hole's the wrong size or shape, you can only adjust it a tiny bit with a file, and drilling is generally out of the question completely, because the parts are often mostly hollow. To make matters worse with 3D printing, errors can be different depending which orientation you print the part. This is because printers often have a combination of different drive methods for different axes. On my printer, a Creality CR10S, the X and Y axis are belt driven, giving them a little springiness which can cause sharp corners to come out a little bulgy. On the other side of the coin, the Z-axis is screw-driven, so it's very accurate. If I were some 3D printing guru, I would probably know the offsets and expansions that my printer produces, but I'm not a super pro printer, so I'm happy to go about my design work in this trial and error way. This video was only short and sweet, because there wasn't much interesting electronic stuff to take a bite into. I hope I managed to give you a little insight into what the mechanical design part of my projects involved instead. Next time we'll have some juicy electronic goodness to have a look at. If you enjoy this video, please do take the time to smash the like button, subscribe button, or ideally both buttons, and I recommend that if this is the first video of mine you're viewing, you take a look at the previous video in the series, where I lay out what this project is all about. I'll pop a link to the video on the screen for you to check out. That's all for today though, so stay safe and have a great day. See you in the next installment.